So you've all found your way once again to the University Lowbrow Astronomers Monthly Meeting, this being the February edition. Bad news is it's February. Good news is the next meeting will be March, and then there's hope. So we're getting there slow. As usual, just as a reminder, we are recording tonight, not broadcast on YouTube, but the recording will be uploaded to YouTube probably tomorrow sometime, whenever Jeff can get to it. So with that, we always have our guest speaker first, and then officer reports. And our guest speaker actually is a club member as well, Claude Pruneau, who has spoken to us. Jesus is at least the third, if not the fourth time, Claude. I think it was four. Yeah, it's four. Yeah. So it just goes to show
you're like you guys.
Yeah. So always great presentation.
You either like me very much or you're a masochist. Or a little bit of both.
I was going to say, can we be both? Anyway, as you probably all know, Claude is a professor, physics professor at our friends just down the road on 94, which we hear is clear tonight, according to Adrian, at Wayne State University. And Claude sent me a little synopsis of tonight's meeting, which I will, there's talk tonight, read to you if I don't fumble it here. One moment. In his abstract is studies of heavy ion collisions at the relativistic heavy ion collider and at the Large Hadron Collider have produced evidence that quark gluon plasma is briefly formed in these collisions. Claude will briefly summarize some of that evidence, but focus on the next step, measuring the properties of this matter, including its viscosity, conductivity, and compressibility. This is a rather difficult task, but he will show that some progress is being made in understanding the equation of state of hot QCD matter and its properties and how it informs us about the properties of the matter present in our universe just after the Big Bang. So with that, go ahead and take it away, Claude.
Thank you. Was I successful in sharing my screen?
I see it.
Yeah.
Looks good.
Okay, well, thanks for the invite again. I've spoken to this group a few times, a couple of times on this very topic. I'm going to try to go a little deeper tonight, since you guys are already familiar with some of this, and show you what we have done essentially in the last decade or so. Mostly at the Large Hadron Collider. There's a lot going on, both at the Large Hadron Collider at CERN in Switzerland, as well as in Long Island Brookhaven National Lab. But I will try to focus on one group of experiments, and actually one main experiment, my experiments at the Large Hadron Collider. So I will try to remind you what this is about and why it's relevant for me to talk to you about this topic, because it has to do with the beginning of the universe. I will briefly show you the experiment, what it does and how it does it, and then we're going to delve into the topic of how we go about finding this new form of matter, QGP, and measure its properties. It's evidently, I'm not going to be able to go into any detail whatsoever, but I'll try to give you a flavor of what this is all about. Well, this is a slide I've used before, and I like to start with this because I like to ask the question, what is the stuff around us made of? What is matter made of? And when we look around us, we see different manifestations, different types of matter. We see different phases, solid, liquid, gas. And if you were able to go in the sun or in the lightning shown here, you would see yet a different form of matter that we call plasma. What I'm going to be talking about tonight is yet another form of plasma even more fundamental form of plasma that we call quark-gluon plasma. And in one way we can explore, and I hope you can see the mouse as I move it, one way we are going to explore this, this new phase of matter, which in fact is not really new. It existed, we believe it existed at the very beginning of the universe. We're going to exploit this machine here, the Large Hadron Collider, to learn about this matter. So I don't know what you know, just let me assume that, and I don't want to insult anybody's intelligence, let me assume you know little about the structure of matter. So everybody knows about atoms, of course, nuclei, I would presume as well. Note that a nucleus is about 10,000 times smaller than the atom itself. And so atoms are basically empty, and all the mass of in the universe is basically into nuclei, and otherwise, you know, even the stuff around us is basically empty. We know already now for several decades that neutrons and protons that compose a nucleus are actually not elementary objects. And we have now a very large body of evidence, and that tells us that neutrons and protons are actually made of particles that we call quark. And the name came from James Joyce novel, and it was created by this fellow here, Murray Gell-Mann, who got the Nobel Prize in 1969 for this discovery. And so, the realm of what I'm talking about tonight is the realm of quarks, where we are now at a scale which is much smaller than the proton or the neutron. You may be familiar with the fact that in nature there are four fundamental forces: gravity that holds us on the planet, the weak nuclear force, which is responsible for the decay of neutrons, and of course also you're familiar with electromagnetic manifestations, photons, light. In fact, you guys are expert at collecting photons from distant objects. But what's relevant tonight is the strong nuclear force, which is acting between nucleons, protons and neutrons, as well as quarks. And this force acts through what we call gluons. And so for the last, I don't know, 6-7 decades or so, perhaps a little more, people have been studying collisions of protons and nuclei and all sorts of things. And we have established a extremely large body of knowledge about what kinds of nuclei exist. And so here at the top, I have a chart of all the known nuclei. And so each type of element exists in different types of isotopes. And so some of them are stable, some of them are unstable, and so on. And so we know that nuclei can exist that are stable. Others can be created fleetingly and decay very, very quickly. And some can even be created to hold a strange particle. But fundamentally, what we end up talking about here is particles that are said to be elementary or were thought to be elementary for a long time. And we classify these into two large categories, what we call baryons, which have a spin 1/2, they're fermions. And we have another type of particle that we call mesons, which have spin 0. And for that reason, there are bosons. Now these particles were, and so here I have a table, this table here shows you a sample of such particles, such fermions, such baryons and mesons, baryons on the left and mesons on the right. But it turns out they're not really actually elementary, and in fact they are composed themselves of quarks, and I'm showing the makeup of these particles here in this table, just as an example. So indeed, we know that deep down there are 6 quarks that are called up, down, charm, strange, top, and bottom. And associated with that, there's also a family of particles that we call leptons, which include the electron, the muon, and yet another lepton that we call the tau. I'm going to focus tonight on what we call quark-gluon plasma. So in that context, we're going to be talking mostly about the properties of quarks at high density and high temperature. If you're looking for a night's, bedtime reading, I would recommend this book here. It's re-edited about every year, and it contains all the properties of all those particles that have been acquired and for the last few decades. And so, so we have knowledge of these particles. Not only do we have knowledge of these particles, but we have a fundamental theory of these particles. This theory is called quantum chromodynamics. It's a mouthful, so we'll call it QCD. This QCD theory is what we call a gauge field theory. That's something that is similar to electrodynamics gauge field theory. And so this is something that is very well established now for, again, several decades. And this theory, and I wrote, if you care about such things, I wrote the Lagrangian density here, just as an illustration that there is a real theory behind this. And what we find with this theory is that when particle collides, they have a coupling. They have an intensity in the way they collide, which depends on the momentum Q, or what we call the momentum transfer. And it turns out this coupling, the strength of this coupling, or if you will, the strength of the force, goes in inverse proportion to the momentum that you're dealing with. So at very low momenta, the coupling is very strong. At very high momenta, the coupling becomes almost vanishing. These three gentlemen at the bottom here, Wilczek, Gross, and Pulitzer, got the Nobel Prize in 2004 for understanding that this type of coupling evolution with momentum means that there is something that we call asymptotic freedom. That is, if you go to very high energy, very high momentum, quarks become quasi-free. Whereas if you go to very low momentum, which is the case of quarks within protons and neutrons, these quarks are completely confined. And so this is the notion of asymptotic freedom and confinement. And these are in opposition to one another, one happening at very low momentum or very low energy, and the other one happening at very high energy. And so with the existence of asymptotic freedom and confinement comes the possibility that if you have a large volume of this QCD matter, you could have actually two types of phases. One at low temperature that we call Hadron phase, which consists of the particles I already mentioned, protons, neutrons, kaons, mesons, and so on and so forth. In one phase at high temperature that we call the quark-gluon plasma. So not assuming that you know much about phases and phase transition, I remind you of the phases of water shown here in this phase diagram. So I have the pressure on the vertical axis, the temperature on the horizontal axis. And so in the three colors shown here, orange and purple and in green, you see the three phases of water. And if you had a given pressure, say 1 atm, and you increase the temperature from a low temperature to a high temperature, you will go successively from a solid to a liquid to a gas. So this is something with, and in fact, it's very timely. There's a storm tonight, so we're all familiar with this. Of interest to mention also is that as the water goes through these transitions at a particular pressure, it takes a while for the matter to transform, the water to transform, because there's such a thing as that we call latent heat, which is an energy required to transform ice into liquid and liquid into vapor. And so this notion of latent heat I will mention again in just a moment, based on this diagram. This is a diagram that was postulated or elaborated based on theoretical ideas already more than 20 years ago. And so what you see here in this diagram is the temperature on the vertical axis and something akin to the density on the horizontal axis. It's actually a baryon chemical potential, but for all practical intent, we can think of it as a density. And what you see in this diagram is a zone. So there's this white line here terminated by what is labeled as a critical point. And this is believed to be a boundary between two phases, a first order phase transition, just like what is experienced by water, between the Hadron gas at low temperature, the low temperature phase, and the quark-gluon plasma on the high temperature, high pressure, high density side of this line. What happens what happened in the universe at the very beginning, we believe, was that as the universe formed, it was at extremely high temperature, extremely high density, but not very large density. And so as the universe expanded, it actually went down in temperature along this line here, eventually coming down across this transition line and forming protons, neutrons, and all the other particles of the zoo that I have already talked about. What's important to know here is that, well, there are two things that I should mention. We have good reason to think that this transition here, shown here as a dashed line, is not a first order phase transition. It's something which means it doesn't have latent heat the way liquefaction does or vaporization does. The other thing I should stress is that instead of what's conventional in the field is to, instead of mentioning or quoting the temperatures in Kelvin, we write them down in terms of MeV. So it was already established more than 20 years ago that this transition at low density would happen around 170 MeV. And of course, you can translate that into Kelvin, and the number is shown here. It's approximately 2 trillion Kelvin. And for context, I'm showing you that this slide here, this picture of the interior of the sun, where now we have good understanding of stellar evolution and so on. And it's understood that the temperature of the core of the sun is something like 15 times to the power 6, 15 million Kelvin. So we're talking of a temperature of transition here from quark-gluon to hadron, which is essentially 100,000 times the temperature of the core of the sun. And so needless to say that producing this type of temperature by conventional means is impossible. It's even impossible for the sun to produce such temperature. So we had to come up with a different way of achieving this. And the way we achieve this is by colliding nuclei at extremely large energy. And this now has been an enterprise for several decades. And there are several facilities in the world involved in studying this phase diagram. And I'm showing here, which is something called the Future Fair experiment. That's an experiment to be, experiments to be starting soon in Germany. But there are also experiments at RIC, at Berkeley National Lab, and the one I'm a member of at the Large Hadron Collider in Geneva. So the big picture, what we're after here is to, in a nutshell, identify this phase transition from Hadron to QGP and back to Hadron. And so we're interested in demonstrating that this deconfinement is possible, that you can basically take the quarks out of the proton or neutron and produce a plasma of quarks and gluons. There are other topics that are of interest, but in the interest of time, I'm not going to go over all of this, but I will mention that once we have established that we have this this production of quark matter. Now we're interested in finding some of its properties. So one of these essential properties is what we call the equation of state. You may be familiar with the equation of state of an ideal gas. For an ideal gas, you have pressure times volume equals the number of moles times the temperature times some constant. So that's PV equal nRT. You may remember from your high school years or college years. And so associated with that, then there are several properties that so it's a matter at very high temperature, very high density. And so we want to know what the properties of this matter are, including, for instance, what is the heat capacity, the conductivity? Is this something that is viscous? Is this something that is compressible, and so on? So this is, of course, as I said already, connected to this group because we have good evidence that the universe formed 13.7, 13.8 billion years ago. This schematic here, this cartoon shows the different stages of evolution of our universe from the very beginning. And I'm not going to go through all of this. I'm sure some of you or all of you are already familiar with some of these many stages. And it's wonderful that, for instance, with something like the James Webb Telescope, we might be able to, look at this epoch here, which is where the galaxies were starting to form. But I'm talking about going even further back in time for about a microsecond at the very beginning of the universe, right after the Big Bang. We have good evidence to think that matter did not exist in the form that we know today. There were no protons, no neutrons, and matter existed in the form of quarks and gluons. And eventually, as the universe expanded and expanded really rapidly, this matter cooled down. And as it cooled down, I'll come back here, as it cooled down, it came across this transition here and formed hadrons. All hadrons mostly decayed and left us, or left the universe with, I should say, basically neutrons and protons. And so, as I said already, the only way we can, to study this in the lab requires such high temperature that the only way we can do this in practice is by colliding nuclei at very high velocity, very high energy. I want to stress that this is a very non-trivial challenge, a very difficult problem to tackle, because first of all, we're talking about colliding nuclei. Nuclei have a size of 20 or so femtometer, that's 10 to the minus 15 meter. And when these nuclei collide, and here they're shown as pancake, essentially because of the special relativity of spatial contraction in the direction of the velocity. And so as these nuclei penetrate one another, the collision will last for about 10 to the minus 22 seconds. Indeed, a very, very short time. So nothing that we can see with the human eye, or even the conventional technologies that we have. The good news is that once such a collision takes place, it will create thousands of particles. So when you have a head-on collision, as illustrated here, at the end of the day, at the end of the collision, more than 6,000, in fact, in some cases, 10,000 particles from a single collision of lead on lead will be created. And we have already observed that at the Large Hadron Collider. Particles that are created are hadrons, leptons, photons, and even the famous gauge bosons like Z bosons and W bosons, even perhaps Higgs, but Higgs would be very hard to find in the mess of these 6,000 plus particles. So needless to say, to see 6,000 particles require an enormous size detector. That means a lot of electronics, complexity. It's very expensive, and to be able to build such detectors, we need very many different skill sets, so that we talk of international collaboration, and that comes both as a strength, as something fun actually, but also as a challenge, because you end up mixing different groups, different countries, and people have different attitudes towards collaboration. So in practice, there are currently 2 facilities where such collisions are studied. The one on top here is the relativistic heavy ion collider, which is still in operation at Brookhaven National Lab. And it features currently the STAR experiment. The Phoenix experiment is retired, but is going to be rejuvenated into what's called S-Phoenix or Super Phoenix. The group I'm actively a member of and participating to is at the Large Hadron Collider, shown at the bottom here. You can see on the right of this image the airport of Geneva, and so that gives you a sense of the scale of this collider. And I should stress that it's deep underground, so it's not it's not a threat or life. It's not life-threatening for the populations that live near Geneva. There are 3 main experiments at the Large Hadron Collider. CMS and ATLAS are truly gigantic experiments. You may be familiar, because you are some of you are connected to University of Michigan. You may be familiar with the ATLAS, the work done by the ATLAS collaboration. There are members of the ATLAS collaboration on the faculty at in the physics department at U of M. I'm a member of this collaboration here, or group at Wayne State is a member of the ATLAS collaboration, and I'm going to show you a little more in a moment about this. But before I show you, I should tell you a little bit about the history and the future of, and without going into any details. And so this here shows you the schedule of essentially the recent schedule and the future schedule. So the Large Hadron Collider started taking data, starting having beam in 2010, and we had a first run that went all the way to 2014, and then successively there were different runs. We just ended a so-called LS2 or long shutdown to do detector upgrades, and we're going to start taking data for a few years, about 3 years. And then and after that, we'll have yet another shutdown, and we'll have further upgrades. And the purpose of these upgrades is to increase what's known as the luminosity, or the probability to have collisions, because the name of the game, particularly in particle physics these days, is to better understand the physics of the Higgs, and also find physics, as we like to say, physics beyond the standard model of particle physics, and trying to understand such things, for instance, as dark matter. So there's a possibility of perhaps creating dark matter at the Large Hadron Collider, and seeing evidence for this. So anyway, so this is just an idea to show you that already a lot has been done, and there's still many years, a couple decades to go in this this wonderful facility. So a little bit more about the detector shown here with 2 human beings at the bottom to give you a sense of scale. This is this showed in red here is a giant magnet, a solenoidal magnet. You see only a cross section of it. And there are many devices within this magnet that are enabling us to detect the particles created by the beam. So the beam come from the right and the left along these yellow arrows, and they collide in the very middle here. And they create 6,000, 10,000 particles. And with this device, we are able to observe these particles. Not only are we able to observe the particles, but we have technology based on this, this main detector called a time projection chamber. We have technology to identify the species of these particles. So this is meant here at the top to give you an idea of how we do this. So particles lose energy in the gas of this time projection chamber. And by plotting this as a function of the momentum of the particle, we can identify their species, pions and kaons and protons, and so on and so forth. We also have what's called the time of flight detectors, which enabled us to measure the speed of the particle. So if you know the speed, if you know the momentum, then you're able to know the mass. And so this is, again, something that we do to identify these particle species. Just to give you an idea of how much work has been done already in a little over 10 years, more than 2,600 papers were shown at conferences by this collaboration, already 621 papers reviewed in peer-reviewed journals, and in excess of 400 PhD theses. And we're just scratching the surface. And so with this image here, I'm trying to show you the beauty and the complexity of the kind of physics we're doing here. This is an event display of the detector. And it shows you in the center here, it shows you with different colors, arbitrary colors. It shows you traces of particles that are created and bent by the supersized magnet. And you can see literally thousands of tracks. And with the naked eye, it's extremely difficult to disentangle all these tracks. But because this TPC is extremely large and equipped with literally hundreds of thousands of sensors, we are able to image these tracks, reconstruct their patterns, their radius, and from their radius get the momentum. And this, of course, takes a lot of computing. So let's get into the topic itself. And to speak about this, I have to first mention that because we are dealing with nuclei, we have to be aware of the fact that nuclei can collide with an impact parameter. So this is illustrated here. And so two nuclei are incoming towards another, and they're separated by some distance, center to center. And this variable b we call the impact parameter. And so as the nuclei collide, so some particles will just go down the beam pipe. We call them the spectators on top and on the bottom. And in the middle here, all the nucleons or the quarks and gluons that are in these nuclei will interact and create this soup of quark gluon plasma, which eventually will become thousands of hadrons. And so we have to be able to have an idea of this impact parameter. And the way we do this is to measure the number of particles that are created essentially perpendicular to the beam, and what we call the central barrel detector. And we also look at how much, essentially how many neutrons and protons end up at 0 degree along the beam pipe. And we have what we call calorimeter to do this. And so depending on the impact parameter, then we will have collisions that will produce very large number of particles at perpendicular to the beam in the central barrel, and then or very few neutrons and protons in the 0 degree detectors. And so consequently, we're able to establish what is approximately the impact parameter of the collisions. What is going to be relevant for the rest of the presentation is that when we do this, we classify the collisions, not so much in terms of impact parameter, but in terms of the fractional cross-section, or if you will, the fractional probability of having these collisions. And so we break it down, for instance, and going 0 to 5 largest multiplicities, so corresponding to the smallest impact parameter, and then we break it down all the way to 5 to 10, 10 to 20, and so on and so forth, all the way down to the smallest multiplicities. Now, I could not have done this 10 years ago or even perhaps 5 years ago, but now I can give you an idea of what we think is happening in these collisions. And so what we think is illustrated, what we think is happening is illustrated in this red box here. And so you have beam A and beam B colliding. They collide here at the origin, and subsequently you form this coagulant plasma, which lives for a little bit, and then the coagulant plasma turns into hadrons, and you may have what we call a mixed phase, a little bit like having water droplet mixed with water vapor. And then eventually this mixed phase becomes hadrons only, and then these hadrons fly into our detectors. And so to visualize what's going on, so I have this little cartoon on the left here. It shows that when two nuclei collide, and again, there is this Lorentz contraction or special relativity effect that says that you have time dilation and spatial contraction in the direction of motion. And the velocities involved here are so enormous that it's really a very, very thin pancake. And so, so as the nuclei collide, they're coming with an energy of multiple TeV, 10 to the power 12 eV, compared to the mass of the proton, which is 1 GeV. So there's a lot more energy coming in the form of kinetic energy than there is in form of mass. And some of this kinetic energy then will be immediately converted into heat and pressure. So this pancake becomes immediately formed with a very high energy density. And because it has this enormous energy density, this pressure gradient will push this matter to expand, and it will look like something that is shown at the bottom. It will progressively expand longitudinally along the beam direction Z, and it will then eventually, this coagulant plasma will eventually transform into hadron. Also relevant to understand is that when you have an impact parameter that is non-zero, as shown here again in this cartoon, you have the two nuclei, green and red, colliding, and you have this region of this intersection that we call the participant. Well, you'll note that this region is asymmetric, and so again here, this asymmetry in energy density will lead to pressure gradient that will provoke an expansion along this x-axis here. And less so along the y-axis. So there is, at the end of the day, a gradation or a hierarchy, if you will, of gradients and expansion velocities in the z direction, the x direction, and the y direction. Obviously, experimentally, we have to figure out how to extract, what is the x and y direction, because obviously, when we collide nuclei, we don't select their orientation. They're too small for us to do that. So what we believe what happens when this type of collision takes place is that as the nuclei cross one another, very, very quickly, a lot of energy of motion, a lot of kinetic energy of motion is transformed into essentially heat. And so when that happens, you will have S quarks, strange quarks, and up and down quarks created. But mostly what happens at the very beginning is the production of a very large number of gluons. And now you have this volume, which is initially very small. And this volume now is going to expand under this pressure gradient. And so as it expands, it will the system will live for an extended period of time, and then eventually it will become too cold to exist as a QGP, and it will transform into hadron. So we have a period of what we call hadronization. And so, okay, I'm going to skip this, and I would like to just show you a little bit of what we've done and give you an idea of what kind of what we've learned. And so with an experiment like the Alice detector that I've just shown you, we can measure particles with exquisite precision. So this is here to show you an example of how we do this. So on the vertical axes here are their differential cross-section. Think of it as the number of particles created at a given PT, which stands for transverse momentum. And so you can see that at very low momentum, there's a lot of particle production, and at higher momentum, there's less. And so this on the left shows the production of pions, and on the right, it shows the production of other types of particles. Well, it also includes pions, but it shows other types of particles, kaons and protons and antiprotons, lambdas and anti-lambdas, and so on. I'm showing this just to illustrate that with this detector, we are capable of basically measuring a large fraction of the particles that exist or known to exist in nature as they are produced in these collisions. And so one of the very first things that was done was to compare what is measured in lead-lead collision to what is measured in proton collision. And so I showed you these cross-section. And so what we do here is we define this quantity called RAA, and we take the ratio of the cross-section in lead-lead, or AA, and then we divide it by the cross-section seen in proton-proton. We have a coefficient to adjust for the geometry of the collisions to account for how many nucleons or many protons and neutrons are colliding. And we're trying to measure this quantity and trying to understand what happens. And so this is actually from the STAR experiment, and that was already taken in 2003, but it illustrates the point very, very well. So shown on the vertical axis is this factor that we call the nuclear modification factor, and it's shown as a function of momentum. Let's focus just first on the bottom right plot. You see that this modification factor is of order 1. And so in these collisions, what I call peripheral collisions, where the impact parameter is very large, there's no modification. This ratio is of order 1. But when we look at the very small impact parameter corresponding to this fraction of the cross section, we see that this ratio, this RAA factor, is now of order 0.2 at large momentum. And so what that means in practice is, and I have to keep the story short, there was a long debate, many verifications of this done by various means, but what we concluded is that we see only a small fraction of the cross section because these particles do not penetrate the medium. The medium that is formed in these collisions is simply too opaque to be penetrated by most particles. And so this one here was at RIC, and we repeated, of course, this same type of measurement in 2010 at the Large Hadron Collider, and we saw similarly here this RAA being very small, of order less than 0.2 actually, and so this suppression of particle production is even larger at the Large Hadron Collider. So we form a very opaque medium. And so with that, we also, we can take all kinds of measurements, and I'm showing here just for illustrative purposes, a spectra of protons and antiprotons in proton-proton collision, p-lead collisions, and lead-lead collisions. And when we look at this, we look at the shape of these spectra as a function of the centrality of the collisions. And what we find, and this is clear from these ratios at the bottom, what is fine is that as you change the collision centrality, as you go from the most peripheral to the most central collisions, large impact parameter to small impact parameter, you find that the slope of these spectra is changing. And what so what that means in practice is the average momentum of the particles is increasing from the most peripheral to the most central collisions. And so again, this now tells us that the system that are produced are essentially very explosive. They expand very, very, very quickly. And so I'm going to skip this, and I'm going to try to give you a little feeling of some of the things we can learn from this. And so I have to take a little detour. I have to talk about the air in the room or the air outside. And so the air in the room where you are sitting is composed of mostly nitrogen, molecular nitrogen and molecular oxygen. These molecules are so small that you don't see them move either, but it turns out that they move at very high velocities. And I thought I had written the velocity somewhere. Yes,
1,000 miles an hour.
yes, basically 1,000 miles per hour. Thank you for paying attention. And it turns out that one can describe the velocity distribution of these molecules thanks to this theory that was formulated by Maxwell and Boseman already more than a century ago. And the velocity distribution looks a little bit like what is shown in this graph. You have the probability of a given velocity as a function of the velocity, and depending on the temperature, the velocities will be small. And if you increase the temperature and make it very large, the velocities will become very large. And so, so this is the velocity distribution for molecules of air at 22 Celsius. So you can imagine that in collisions, it's going to be a little different. In nucleus-nucleus collision, it's going to be a little different. Whoops. There we go. And so, what we do is we look at these momentum spectra. I have one here again on the left, the bottom left. And this is actually from anti-deuteron, the antimatter of deuteron. And we have a model to account for the temperature of these particles, but we also have to take into account the fact that, well, this is not a closed room. This room doesn't have walls. This cartoon here is meant to illustrate a nucleus that has a coagulant plasma that is extremely hot, and it's expanding really fast. So this blue box here represents a fluid cell, a component of this coagulant plasma, and this cell has been accelerated by the pressure gradient, and it's moving outward at very high velocity. And so within the cell, there is what we think is coagulant plasma that is at some high temperature. And on top of that, this cell now is being accelerated, being pushed outward. And so when we try to understand the spectra of particles that we measure, we have to account both for this expansion of the system as well as its temperature. The mathematics is shown here at the top. We don't have to focus on that. But what the outcome is that we can then model this, we can do fits. And at the end of the day, what we find is that is illustrated in the graph at the right, where we have the temperature and the velocity of the particles, or the velocity of expansion, I should say, for different systems. And so we can, what we see is that when you have, so this region here is for lead. So we find that depending on the impact parameter, you'll have slightly different temperatures, and that's basically in the details that I don't want to get into. But what I really want to bring your attention to is the scale. And so this is 0.12 GeV, which is 120 MeV. So the temperature is indeed very high. And the horizontal scale here tells you that these systems basically are expanding. This blue box here is expanding at something like 50, 60%, perhaps even a larger fraction of the speed of light. And so indeed, we have a system that is very explosive. It's expanding really quickly, and it's very hot. We can learn even more about this system by looking at the relative abundances of particles that are produced. And so again, here we can invoke thermal physics, thermodynamics, and we can formulate, if you care for such details, partition functions, and we can formulate what should be the density or the number, if you will, of particles produced at a given temperature. So we have models to do this. So what we do, we observe all the particles that are listed here on this slide: pions, kaons, phi mesons, protons, antiprotons, lambda baryons. and so on. All of these, including helium-3, anti-helium-3, even anti-helium-4. And we can calculate based on our on the relative abundances that we see, what is the temperature of the system. So we model this with this this theory of basically this thermodynamics model. And this thermodynamic model gives us the expected abundances for all of these species. And so in this plot, you have squares that are showing the measured data, and you have bars that show you the outcome of our fit, the outcome of our model. And what is important, again, is to look at what is the temperature that this model returns at the end of the day, at the end of the fits. And again, it's of the order of 2 × 10⁻12 Kelvin. And so indeed, the system that we form is opaque. It's expanding really rapidly, and it's produced at a very high temperature. And so, so based on this, this gives us some reason to believe that there was, before the emission of particles, there was a transition from a QGP to a Hadron gas. How do we achieve this conclusion? Requires a little more work, and I'll try to give you one example of how this was achieved, if you give me a couple more minutes. And one way to do this is to measure something known as anisotropic flow. Shown here in the center, at the top here, is a cartoon that shows the cross-section of 2 colliding nuclei. You have different colors. Essentially, the purple colored circles illustrate the nucleons that are participating in the collision. The yellow and orange nucleon are, I remind you, they're not affected by the collision. The collision is actually happening too fast. So these nucleons are just going down the pipe. They're not participating in the collision. So at the end of the day, we have a system consisting of these purple nucleons. And you can see that this system is not isotropic. It's not a circular blob. And because it is not isotropic, it will expand under the tremendous pressure within the system and into the vacuum in different ways. And so the largest gradient is along this direction that we call psi2 here, and the smallest gradient will be along the other direction, perpendicular to it. And so what that means in practice is that particles will be produced anisotropically in the transverse plane to the beam. And we model this particle production according to this expression. So here, this is for those of you who might like mathematics, this is what we call a Fourier expansion. And so we model the emission of the particles at an angle phi relative to this symmetry plane that we call psi2 here. And we write this as a Fourier decomposition. So there are these coefficient Vn, V sub n here, that describe how, what the symmetry, what the component of these different orders of cosine and phi minus psi. And I have this cartoon at the bottom here on the right that shows you the contribution from these different orders. So V1 is what we call direct flow, directed flow. V2 is the most important component that is produced in these collisions. That's what we call elliptic flow. And then smaller components are triangular flow and quadrangular flow. But the point of this is to really illustrate that as the system expands, it's producing particles in the vacuum, but in a non-isotropic way. And we have developed tons of techniques to measure this emission, the anisotropy of this emission. And then we can then measure these coefficients with very high precision. These coefficients, it turns out, are determined by the spatial anisotropy of the system. So this blob here, again, showing you the participant region, has an anisotropy in the transverse plane. we can characterize this mathematically as an eccentricity. The definition is shown here. And what we find with models, hydrodynamics model in particular, that are now known to explain these collisions very well, we find that this elliptic flow V2 is essentially proportional to the eccentricity, the spatial eccentricity that we call epsilon2. And so basically the amount of V2 that we see tells us about the really about the expansion of the system as it proceeds from the initial state of the collision. The bottom actually, it's not a cartoon, it's actually a calculation. It shows you what happens as the system evolves. The units are shown here as Fm over c. Fm is Fermi, c is the speed of light, so Fm over c is a time, and that amounts to 3.3 times 10 to the minus 23 seconds. So this illustrates that the system is expanding really rapidly and effectively explodes. And so here is an illustration of measurements that were done of this. And so this is a measurement of several of these coefficients, V2, elliptic flow, V3, V4, and I will just focus on V2, the top here, which is the largest coefficient, as a function of this fractional cross section. And so as 0 corresponds to 0 here corresponds to the most central collision, 0 impact parameter, and 50 corresponds to large impact parameter. And you can see that there's this large value of V2, and it tells us that there's really a push, an anisotropic push in expanding medium. And so what we do is now we use hydrodynamical models, hydrodynamics, and we can then simulate and describe the expansion of this system. When we do this in the models, we can then compute what is the expected Vn, V sub n, in this case, V sub 2 coefficient. And you see that in this particular calculation from a colleague of mine at McGill University in Montreal, there is a very good agreement between the data and the model. I should stress, however, that to achieve this agreement, these folks had to introduce something known as viscosity or viscous flow within the calculation. And I'm going to skip another slide and show you this here, just to illustrate that we are now at the point of measuring the properties of this coagulant plasma, one of which is the shear viscosity. So viscosity, if you're not familiar, is something that relates to the capacity to transfer momentum perpendicular to the direction of flow. So if you have, consider the cartoon at the top here, if you have water, say, flowing in a pipe, and on one side you have water flowing faster than the water flowing on the other side, if there is no friction whatsoever, then the water on, the orange arrow and the blue arrow will remain, the velocities will remain. Without friction, these velocities are not, these flows are not impacting one another. On the other hand, if you do have friction, and in water, it doesn't feel like it when you shower or take a bath, but there is, in fact, a little bit of friction. And so what the impact of this friction is that if you start with flows that have different velocities, after a while, these flows will interact with one another. The fast one will become slower, the slow one will become faster, and you end up with a system that is equilibrated. And so what we find is that nuclear matter has this property of being slightly, ever so slightly viscous. This here shows calculation, but I'm going to skip this discussion and go to a demonstration of the impact of this viscosity. So this was measured already some years ago in lead-lead collisions. And we measured the data. The data is shown with points, blue points, triangles, and red points corresponding to different coefficients. And the dashed line and solid line correspond to calculations, hydrodynamics calculation with different coefficient of viscosity. And you can see that we have to invoke a little bit of viscosity to be able to explain, in particular, this V3 coefficient, these V3 coefficients. Without viscosity, we cannot really explain the magnitude of these coefficients. And so this tells us indeed that there is viscous, there are viscous effects in these collisions. And so the shear viscosity is something that we can measure now very well, and there has been a lot of work on this. And this cartoon at the top shows you how the precision, I apologize for the poor quality of this cartoon, but it's meant to show that we have learned how to do this experimentally and theoretically, and we now have reached very good precision for this particular property of the system. And shown at the bottom left here is a recent paper by colleagues of mine, and they show that we now have an understanding that this eta over S, the shear viscosity per unit of entropy, has this kind of dependence on the temperature of the QGP. Now, if I left you with this, you would say, so what? Well, I have to try to impress you a little bit by showing this bottom graph here on the right, which compare eta over S, this shear viscosity per unit entropy of different substances. And so in pink here is water. And so this is plotted as a function of the temperature relative to the critical temperature. So you have water here. So water is not very viscous, but still it has finite viscosity in this scale. You have helium here, which helium at very low temperature is known to be a superfluid, and yet it's not perfectly, it's not a perfect fluid. It has a little bit of viscosity. And what we find is that the systems, the QGP systems we produce in RHIC collision at Brookhaven National Lab and collisions at the Large Hadron Collider are at this very, very low viscosity here at the very bottom of this plot. And so we have systems that are extremely high temperature, extremely high density. They're essentially opaque, extremely interacting. They are exploding, essentially. And yet they have this amazingly small viscosity. And so viscosity is one of the many properties we are investigating. So there's the shear viscosity, there's the so-called bulk viscosity corresponding to what's known as the Young modulus for macroscopic object. There are other properties like the compressibility, the heat capacity. We are essentially just scratching the surface. We are beginning to try to measure these things. So I'm going to stop here. So just to summarize, I've tried to show you that we are having very much success in the study of heavy ion collisions. We think, established that some flavor of QCD matter is in fact formed in these collisions. QGP matter is formed. And to prove this scientifically would take me many hours, and you might be able to debate, different points, and in the field we are still arguing about all these points, but we have good evidence at least that we have very opaque system that flow very fast and are extremely high temperature. So a state of matter that is very, very different from the state of matter that we're familiar with. And so as we proceed to understand this state of matter, we're now getting to the point that we measure its properties. I've given you an example of measurements of shear viscosity, but we also have techniques to, and this is something that I do in my group, we have techniques to measure diffusivity, compressibility, and so we are, we're just essentially beginning our journey to understand this type of matter, and hopefully, as we understand it, it will inform us about the conditions that prevail at the very beginning of the universe.
No, I mean, no other problems, no other symptoms. The only reason I really noticed this is because I can hear my heartbeat in my ear. And I was checking my blood pressure today, and that's what I noticed it was doing. Loud, quiet, missing, loud, quiet, missing. That's what I just started noticing. But it's reverted back to normal again, and so I'm not doing anything.
I'm having a hard time hearing you. I'm sorry.
Kathy's unmuted.
About 45 minutes, maybe an hour.
That may not have been in a question.
Right. It went back to normal, maybe an hour.
Very interesting presentation. Thank you very much.
Oh, my pleasure. Do you have any questions? I was trying to give you an overview of the things we do. It's very hard to hopefully this gives you an idea of the stuff that we do. And I'm just scratching the surface.
Your last presentation was about 3 years ago, I think.
Something
4
like
years
that.
ago. And I'm still trying to catch up with that one. And now this really takes up where that one left off. And now I've got another 3 or 4 years of trying to assimilate all of this. But it's fascinating stuff.
Thank you, Ken.
I got a question. Well, it's got 2 parts, I guess. One, are there many high energy photons also created during these collisions? And 2, if there are, do they affect the way the particles move at all? I mean, could that also be part of the source of the viscosity?
So the answer is yes and yes. There are two sources of photons that are produced by approximately 2 sources of photons in these collisions. There are photons that are produced by the decay of hadrons. For instance, the neutral pion spontaneously decays into 2 photons. That's not very interesting because it's actually it constitutes a background for us, the more interesting photons. And so this quark-gluon plasma consists of gluons. Gluons are neutral, but it also involves quarks, and quarks have charges of 1/3 or 2/3, plus 1/3, plus minus 2/3. And so these charges are now, as I showed you, are produced at extremely high temperature. And so think about the air in the room moving at 1,000 miles per hour. These charges now are moving back and forth, within this small, very tiny system. They're moving at a very large fraction of the speed of light back and forth. And so they become, think of it as an antenna. They are emitting electromagnetic radiation. And this radiation is essentially gamma rays, photons of very high energy. And in fact, one of the important component of the measurements that were conducted both at Brookhaven National Lab and at the Large Hadron Collider was to measure these what we call direct photons that are emitted by the QGP itself, not by the decay of hadrons like pions decaying, but measuring these photons directly. And that extremely difficult task, because you have to first identify all the photons from decays. You have to tag them, so to speak. It's actually done statistically. You can't do it one by one. But at the end of the day, people were able to measure the energy or momentum spectrum of direct photons. And once you have that spectrum, you can actually determine the energy of the system as it emitted those photons. When what I showed you is the spectra of pions and protons and so on. These particles are emitted when the system is cold, when it's decoupling, and it's, you know, the quark-gluon plasma is turning into hadrons. And so at that time, the system is already a little cold. But with photons, the system is producing these direct photons when it's already just being formed. And we have evidence now that the temperature at that time measured with photon is of the order of 400 MeV. Not, you know, so basically more than twice the temperature of the particles that I've talked about today.
I have a simple question, maybe not so simple. If I take a combination of 3 up and down quarks that together weigh about 10 MeV and put them together, I get a proton or a neutron that weighs like a GeV. How does that happen?
That's a very good question. And so that has been a quote unquote mystery for a long time. So so when we think of quarks, we have actually 2 ways of thinking of them. We have what we call the current quarks, the quarks that appear in the theory. And those, as you just pointed out, they are 5, 10 MeV. And when you sum their mass, you don't get the total mass of the proton. But we also like to think in terms of constituent quarks. So we take the mass of the proton divided by 3, and then we say each quark has a mass of 300 MeV or so. But I'm not answering your question. So what you might ask then is, where is this difference? We are pretty convinced that these quarks have very low mass. And yet we also know that the proton has a very large mass. So what's the difference? Well, the difference is the gluons. The gluons, in spite of being massless themselves, the way they interact, the way they are pushed, what you have to realize is that we think we think of the universe around us as vacuum. Yes, it's vacuum, but it's also a soup of quarks, virtual quarks and virtual gluons at very low temperature. And so the quarks that are within the proton are essentially fighting against this vacuum. They're pushed, they're maintained within the bag that constitute the proton. And this interaction with the vacuum generates a mass. It's a simplified way of putting it, but it generates a mass and basically almost the entirety of the proton mass, and similarly for the neutron. And so it's what we call a dynamic mass. It doesn't come from the sum of the constituents, really. It comes from something more complicated. I should stress that we now have a theory based on quantum chromodynamics. Calculation in that theory are very difficult. They cannot be done by so-called perturbation techniques, and they need to be done on massive computers. Each computation takes days, but these computation now have been able to show unequivocally that this theory QCD is capable of actually predicting with very high precision the mass of the proton. And as I said, it's not, this mass comes from the interaction of the quarks and gluons within the proton with their surrounding.
Would it be reasonable to say that the extra mass is basically the mass equivalent of the binding energy of the proton? Yes and no. If you think of hydrogen, the atom of hydrogen, it's made of a proton and which is the nucleus of the atom, and an electron. And so when you take the sum of the mass of the proton and the electron separately, you get a certain value. The actual mass of hydrogen is slightly below the sum of the mass of the proton and the mass of the electron.
To be precise, it's 13.6 electron volts smaller, very, very small value compared to the mass of the proton. And so here it's the binding energy, the Coulomb force, the attractive Coulomb force is giving this binding energy, and it's producing this shrinking mass, if you will. In the case of gluon, you can argue it's something similar, but given that gluons have no mass and the quarks inside have no mass, it's one should be careful the way one formulates this equivalence. It's not a real equivalence, but yes, you can think it of in some way in terms of binding energy. I mean, there's a model that was formulated at MIT called the MIT bag model, which essentially says that you have 3 quarks inside a bag, and these 3 quarks have velocities, and they're colliding with the bag itself, and they're confined by the vacuum. And so it's really an interaction between the vacuum and the quarks inside.
We have a question from the
My
chat.
theoretical physicist friends would probably kill me for saying something like this, but yeah, I think in a nutshell, that's what it is.
We have a question on the chat, and it says, in the mixed phase region before quarks completely transform into hadron, can diffraction techniques be used to reveal the phases present? And is the event time or spatial extent too small to allow this diagnostic?
So that's the answer is no, it cannot be used, and the answer is yes, it's too short. And so the size of the system is we're talking of a system that is the size of a nucleus or barely larger, and that lives for 10 to the minus 22 seconds. You know, computers nowadays have these tremendous speed. We can now do calculation, you know, at gigahertz, and so we have the capacity to generate oscillations, and in a circuit at the speed of 10 to the power 9, 10 to the power 10 oscillations per second. That's the limit of what we can achieve today. Perhaps in the future computers will go faster. They tend to do that, but you know, we're talking of time scales that we can comprehend and measure macroscopically of the order of 10 to the minus 10, maybe 10 to the minus 12 seconds, picoseconds, and the system we're talking about here is 10 to the minus 22, so 10 orders of magnitudes shorter in time. And so it's impossible to probe the system directly, and you know, refraction, diffraction, that sort of thing. Certainly not directly. There are effects of refraction in collisions, but that's a totally different story, and discussing this would take us far afield. But the short answer is no. The only way we can see this plasma is through the very sophisticated measurements of you know, measuring the momentum spectrum, the anisotropy of production, and there are various types of correlation functions that we study that would. I wish I could talk about it, but I mean, it would take us the better part of an hour to introduce you to these correlation functions. But if you're interested, since I wrote the book, I have a book on this. So these technologies, these mathematics for measurement of these particles is actually covered in my book.
Is the environment that you're studying, is it possible that it also allow detection maybe of gravitons?
Gravitons, no. The scale, no, not gravitons, but there are there are efforts to measure different types of particles, or so-called the extension to the standard models. And so such things as dark matter particles. You're as an astronomer, you're familiar with the existence of dark matter. We're all, we know about dark matter already for almost 100 years, but we still don't know what it is. But there are some theoretical considerations that tell us that dark matter could in fact be, under certain circumstances, depending on its nature. But there's some theory that said that dark matter can in fact be produced at the Large Hadron Collider. There are other types of particles, such as strangelets, that are massive strange particles. There are a number of speculations of such things as leptoquarks, composite leptons that have been predicted. And there are considerations that tell us that if these things exist, they could be measured at the Large Hadron Collider. But to my understanding, gravitons, no, cannot be measured. However, we can now see with LIGO and Virgo, we can now see manifestation of gravitational waves, and that's pretty awesome.
Any other questions for Claude?
If I could ask more of a nuts and bolts question.
Of course.
My understanding is the detectors like your Atlas, Alice are so incredibly complex, but the collisions are happening so fast and so many pieces are flying everywhere that you can't possibly record all the data. So is it true that there are lots and lots of hardware triggers that are throwing away most of the data before you even get a chance to decide, this is something interesting, this is what I want to save?
That's absolutely correct. And so Atlas and CMS have, by and large, different goals than us, Alice, although they have a small contingent of heavy ion physicists. So every time that we have heavy ion beams, there are some people on these two experiments that are actually spending time taking data to study these collisions. But their focus is really proton-proton collisions. And indeed, the intensity of the beams and the intensity of the beam has been increased now since the last shutdown, and will be increased again in the next shutdown in 4 years. And we're reaching luminosities, or if you will, a rate of collisions that are so enormous that it's absolutely impossible to record everything. And so there are now technologies that are called triggers. Well, these technologies have existed for a while, but Atlas and CMS have developed all kinds of triggers to be able to focus on the specific types of collisions they're interested in. And so they will spend some fraction of the time accepting all the collisions to do what we call minimum bias physics, to accept everything with no bias or minimum bias. But the majority of their time is spent with very specific types of trigger based on hardware, as well as on very fast computer, massive farms of computers to calculate on the fly what is being detected and whether it should be kept or left to disappear. And so the amount of technology involved in these, the amount of computer and computing is just, it's tremendous. It's mind-boggling.
Do you not use a similar technique with the Alice experiment?
We with the Alice experiment, we just went through. For us, it's the other way around. We the collisions that we detect are so complex that it's actually very hard to select those that would be potentially more interesting than the others, because we're interested in different questions, and so we formulate our triggers in slightly different ways. Basically, we are taking minimum bias data most of the time. Not entirely, but most of the time. We have some interested in what's known as jet physics, understanding, and this is a whole area that I didn't even touch in the presentation. So when quarks interact very violently, they exit the system. They come out of the collision region with a lot of energy, and as they escape, they form what's known as jets. Measuring these jets tell us about. We know that these jets interact with the medium when they interact with the quark-gluon plasma, and so seeing how the jets are modified by their interaction tells us about the properties of the quark-gluon plasma. So we have some triggers to do that, but by and large, we now have this new technology that we are almost capable of taking and writing all events. We haven't been able to do that yet, but we are working towards that. And so that we will be able to amass billions of collisions, which is already what ATLAS and CMS are doing. Our detector, this time projection chamber, is a fairly slow detector. And as particles come through the volume of this detector, there's a gas, and they ionize the gas, and these electrons have to drift through the gas, and so this whole process takes several microseconds, and so that makes for a very slow detector. So it limits the rate at which we can take data, and so we are effectively able to take pretty much everything.
So how many events per second would you normally be capturing?
Oh gosh, I used to know this. We were in the range of 100 events per second.
Okay.
But I think now we should be, with the upgrades, we should be able to do 10 times that. But that's a fraction, a tiny fraction of what ATLAS and CMS do. They they can run a lot faster. How fast, I actually don't know, but I'm sure they can do tens of thousands per second. Even in the megahertz. I would think they can do megahertz.
I used to help the ATLAS people with the networking for here. And as I recall, this is about 7 or 8 years ago, they were collecting on the order of 1 terabyte per second of data.
Oh yeah. So do we.
Yeah.
But it's just the collisions they're collecting are different. And so these proton-proton collisions have 50, 100, sometimes 200 particles, and our collisions have 6,000, 10,000 particles. So that gives us different data volumes.
Mm-hmm.
But in the computing facility at CERN now, they have storage in several petabytes of disks to store all the collisions that have been taken since the beginning. And now, people are starting to think about, well, what is it that we can give up? What is it that we're not going to keep on disk and we're going to put on long-term storage?
Any more questions for Claude? Okay. Thanks once again, Claude. Much appreciated.
My pleasure. I'm going to stay around, but first I'm going to go get a glass of wine.
I was going to see if he could switch the view here. Well, that's okay. Get him when he comes back. Anyway, well, my next thing is I was going to ask him what he needs for a cap or shirt or whatever, but I'll try to remember that. So
he's an honorary member, and this is his 4th time. I don't know what we can offer, Charlie.
Well, usually if they don't take a hat or a shirt, or we've given them both, then we go with like a restaurant gift certificate.
Yes, we did that one time. That's right. Okay.
Yeah,
got
we
it.
probably did that already too.
Yeah,
We
yes,
can always
we
do it
did.
again. Yeah.
Okay, yeah.
So anyway, until Claude gets back, I will move on. Two things I've got, and I'm actually going to call on two non-officers on this. First one is John Wallbank, who, by the way, is now the president of astronomy at the beach. Thank you, Adrian. Congratulations. Or not Adrian, John. Adrian was the president. He's now the secretary. I'm treasurer. I'll get this right.
You can congratulate me for stepping out of the position if you would like.
There you go.
I'll accept
Thanks,
that.
Adrian.
But you're still stuck as an officer. So anyway,
yeah.
John, would you like to describe your communication with Chromane and how we can help you?
Oh, the Chromane Library in Heartland wants a presentation in April. They offered a number of dates, and the librarian for adult services there thinks that the Webb telescope would be an excellent topic. So if someone wants to contribute to that, I plan on putting together a PowerPoint that covers, well, I had a laundry list of topics that are somewhat parochial but broad interest, and someone wants to assist with that, that would be welcomed.
Thank you, John.
Let's say while we're on the topic of GLAC, we did have our elections in January. John Wallbank was stepped up as president. Tim Campbell from the Ford Group, the Ford, I can't remember their acronym, Astronomy Society, something like that. He's our vice president this year. I'm staying on as secretary. Adrian is stepping over to be treasurer. And our director of communications is Bob Tremblay, and he's got basically help from Brian Autumn as kind of our past communications guy, and Mike Ryan. And in the process, we basically came up with a planning committee, an actual committee to do the AATB heavy lifting, which consists of the officers and directors plus Harry Anderson, Bill Slogeris, and James Lawless. And I believe those are all three lowbrows. So lowbrows continue to have good representation with GLAC.
So I thought Bill Slogeris was also a WAS member. So
Could
it's
actually Slogeris is secretary of Oakland Astronomy Club. I'm incorrect.
And also a WAS member and a lowbrow member.
So yeah, you've done what I did, which was become a couple of different. We have a few people that are members of different clubs. So join. You're in the multiple club.
And we're planning an in-person event at Island Lake State Park. They say that they are doing live events there now, in-person events. There's no restrictions on numbers of participants. We're playing this by ear. We know that there are unforeseen contingencies, but we right now, as we're moving forward with an event on the ground, and we're looking forward to a whole lot of people with telescopes being there, and we're looking forward to being able to implement a really good event.
Yep, September 16th and 17th, if memory serves.
Correct.
So I'll go
back,
ahead. Whoop, I was
John,
gonna go ahead
back.
and ask,
Go ahead, Adrian.
I was going to ask the question to you, John, from the lowbrows. Are you looking at bringing back speakers, or considering just doing the kind of the back to the basics that we were thinking of doing last year, with just making it about telescopes?
That depends on decisions made at our next board meeting. We have a lot of information to collate regarding facilities and finances and such, We do have one speaker, and we will have to decide how that speaker is going to present, whether it will be an
True.
online or an in-person event. Yes.
Nope, that's very true. We convinced I forget her name, Nicole Zellner, I think,
Yes.
said that she would speak at the AATB, which that would be great. So
Yeah, she was going to be our lowbrow September speaker, but since AATB and our lowbrow meeting are the same night, being Friday night, then we're not going to do the meeting. And yeah, you're right, Adrian. She was very nice to say that she would do AATB instead.
Well,
Worked
she
out.
has done it. I think it's been, what did she
Yeah.
say, 4 weeks ago? She
Yeah.
was a speaker there for both nights, so,
Mhm.
yeah.
Okay. So my next item was that we Thursday or Wednesday evening had a meeting with a gentleman that wanted to talk to us about having better access for people, say in wheelchairs at Peach Mountain. And Jim sort of headed up that conversation, set up the Zoom meeting. Jeff also has some minutes from that meeting that if you wanted to maybe share those,
I can
share
do
your
that.
screen on those, Jeff and Jim. You're
Yes.
going to give us a lowdown?
Well, Joseph Willett contacted us asking about accessible venues for looking through telescopes. And the only one I know of is on the roof of Angel Hall. You know, people in wheelchairs or otherwise compromised in their mobility can get on an elevator and, you know, shuffle their walkers off on the roof or roll their chairs out and observe. Everyone else is pretty much in the same boat as the lowbrows, except some of the observing sites might be more amenable. I remember observing with the Ford Club at Island Lake, and they were in the parking lot, and there were telescopes all over the place, and it was basically an open house. And you know, that a site like that could work very well for being accessible as long as the group hosting the event was prepared. And that's the same with us up on Peach Mountain. We can do certain things like set up scopes up top along the asphalt road or in one of the parking lots if we know there are people that would be using them. But Joseph was interested in making the observatory more accessible, and that is a lot bigger challenge. And when he went in that direction through the email conversation, I made it clear to him that there was a lot of willing but no money. And so apparently he has access to grants and foundations that might be interested in a project like this. And so our next step is when the weather breaks and we've got some firm ground out on Peach Mountain, we'll meet Joseph out there and he'll be able to assess the situation directly rather than through the photographs we showed him, or that Jack showed him on Wednesday night. Because those of you who've been out to the observatory do probably have a pretty good understanding the challenge it would be to get wheelchairs in and out, and not only of the building, but just down to the building. So, and we went through all of these as best we could without being on site with Joseph. And he has a construction background, so he's pretty aware of what might be necessary. And, you know, doing a site visit, I think will produce some pretty good ideas or mix the thing all together. But I think there are things we can do that if we've got the funding, we'd be more than happy to do. Like, you know, have a lift platform as opposed to the ladder we have in there now. That was one of the things he suggested. But there were several of us there, so you know, any of the rest of you that have comments, just jump right in.
Yeah, I think that was a pretty good summary, Jim.
Yeah.
Really, I think this is really an opportunity, the way I see it, if there's something that we can do as the club to really, you know, make that more handicap accessible, I just think that's a tremendous thing to do for the community.
Well, I agree. You know, many of us are probably have life experiences like mine, you know, having had people in and out of their lives who would have been thrilled to, you know, go look through a telescope if it was at all possible to do so. So yeah, it would.
Yeah.
It would be a good thing for the club to do, and it would be a good thing for the community to know that we had the facility for them to come and visit.
Exactly.
One thing I should add, my life partner suggested that we look into a composting toilet, because there are no facilities out there, and you know, we're asking, you know, first there's the entire class of females that observing out there is very difficult because there are no facilities, and now we're talking about wheelchair bound and other mobility compromised individuals, and that just can't wander out into the woods. So that I think we need to add to, you know, this sort of project. And Jenna suggested a composting toilet mainly because it didn't need plumbing and it didn't need a lot of maintenance. And you know, somebody'd have to go out there and, you know, hose it down every once in a while, but other than that, it should be a, you know, another thing that we could do to make the site more accessible and welcoming to the general public.
Yes, I'd like to add one thing. So we talked a little bit, what Jim just talked a little bit about access to the eyepiece once in the observatory. I think the other issue that we talked about was getting to the observatory. So you have that long 2-track dirt road, which is, that'd be a challenge to get someone down there in a wheelchair. And then if you even got to the observatory, then you have to get up into the observatory. And we do have the ramp, and we have some other, you know, ways to get it in with help, but that could probably be improved. And it's just another thing that when Joe is there to actually see things in person and see what it really looks like, he would have maybe some additional ideas on what we might want to be able to do there. But that 2-track is treacherous even in the dark by just walking.
Yeah.
the last time I was there.
Yeah, we did talk about, walking vehicles down there. And we have done that in the past for mobility compromised people. We've walked their vehicles down there so that they could disembark near the building, but still getting around the grounds around the observatory on anything except your 2 feet is an adventure.
Thank you, Jim.
Yeah.
Okay. Jeff, could you switch back to the other view so we can see everybody's view? That just helps make sure I see all the officers, in case anybody's dropped out or come in.
Yeah, the view is controlled by you, actually.
By me?
Yeah.
Go to gallery.
Claude's still screen sharing.
No, wait a minute. Did I
No,
just
he's
do it?
not.
Oh, just go to gallery view.
Yeah, well, that switched mine, but I don't think it affected anybody else.
Oh, yeah. I'm good.
No,
Okay,
Claude
yeah.
is not, Claude's not screen sharing any longer.
Yeah, I was the one that asked for it and I did do it, so. Yeah, but I think that's it. You're right. He was the one that invoked it, so. At any rate, but apparently we can override. If anybody does want to see their entire or everybody's screen, just go up there to view. And if you left click that, select gallery, and then you'll see the everybody's little window there. Anyway, so we'll move on to officer reports. I will pick on Joy first.
I've been updating back and forth whether it's live or it's not live. I keep changing them back and forth, it seems, day to day. But so if I could figure out what to put for next month, that would be great.
My thinking is that we'll probably try to go with hybrid next month.
That's what I was gonna say.
Yeah,
Right.
COVID numbers are coming down. Hopefully the weather will be better, so we'll see. That's my thinking, but I'm not the only one deciding. So I will check with Shannon though to make sure we do have a key code and all that. I think we were set up for the first 3 months of the year, but it'd be nice to know that for sure. So I will find out. Adrian.
Well, if we don't use the rooms, the dance troops will. So that's one incentive to get out. The roads were clear, so we probably could have done it, but there's nothing wrong with having the meeting at all. Nothing in particular lowbrow to report. Special interest wise, it did get clear enough for me to test my tracker tonight. That doesn't have to go into the minutes, but I do have some shots to look over later. But other than that, just I'm in a few different clubs, and still may have access to some speakers due to the Explore Scientific connection that I now have. So I know we're looking for speakers. The Warren Astronomical Society is looking for speakers. It's just something I need to pull the trigger on to see if some of these ladies and gentlemen might be willing to give us talks where there's some holes to fill. That would include David Eicher, who's, I think, chief editor of Astronomy Magazine, David Levy. There's an astronomer, John Quinn, that sometimes comes on, and a host of Astronomical League members that help out, and even Scott Roberts himself, president of Explore Scientific. There are a few young children that do an awesome job with their presentations. And we have Kareem Jaffer, who comes to us from RASC Montreal. And I think he's already set up for a talk. I don't know if Kareem is here tonight, but so there's a host of speakers that I could talk to, and if you would like, I can kind of put a feeler out to the group and let them know Dave, I can get dates from you and put a feeler out, see if any of them might be interested in giving some sort of a presentation. So that's it.
Thank you, Adrian. And before I forget, we did run into an issue with our March speaker. I had noticed that we had him on the schedule marked as tentative. So I got a hold of him. It was Professor Michael Meyer from the U of M. And he was going to do a talk on the James Webb Telescope. And I thought, how timely. But that's also probably what got us, because some little entity called Saturday Morning Physics got him. No, I think what he's trying to tell me is that that's probably the Saturday morning right after our meeting. And he didn't want to have two talks like that close together. So anyway, I've asked him if he's interested in moving to November, because he did ask if we had anything open in the fall. I have not heard yet, but that left an opening for March, which Adrian has kindly decided to fill with a talk about a, spoiler alert, I'll say nothing more, a book he's writing. So anyway, a few of us that joined early saw a little, heard a little bit about that anyway, but thank you, Adrian. In fact, actually, Adrian, I believe you're our March and April speaker, no?
I might be, because I think I'm filling in, sharing book stuff. The book that I'm writing about Point of Park, Lighthouse Park, in April is patient that I've been for just travels to all different types of skies in Michigan and beyond. So yeah, so I'm pretty sure the attendance will probably drop for March and April, but that's okay. Those of you that come out, hopefully you'll enjoy it.
Thank you. Amy, I think I saw you there someplace.
Yeah, I'm here.
There you are. Anything new on the newsletter front?
No, other than just, I guess I would like to say, if you have ideas, and please send them to me for the newsletter. Thanks for everything that has been sent so far. And if if there's a type of thing you want to see in the newsletter, I'm looking forward to seeing that, and I hope you will submit it. So that's it.
Amy, didn't I promise to try and start some sort of section on traveling and nightscape imaging?
You did.
Yeah, and I forget exactly what I think was the idea. Basically, here's a site that I've been at, and here's what I like about it. It's something like that.
Yeah, something like that, and we can email on that. Yeah.
Yeah, I gotta get to work on that. So, all right.
Thank you.
Yep. Thanks for the reminder.
Thank you. Before I forget, can you hear us, Claude? Are you there, Claude? I'll try him one more time. If not, I'll email him. We're going to give him something, darn it. Anyway, how about Dave Jorgensen?
I have nothing to report.
Wow, that was quick. Thank you, Dave. But he is taking the minutes. We appreciate that.
Yeah.
How about the guy with our money, Doug?
The guy with the money says, I think we still have the same number of memberships, 177 it looks like, and still the 13 we're carrying. So people are paying up, and we're getting trickle of new members. I always try to send out a notice when we get a new member. So $12,505 in the treasury. 400 of that is still waiting to be paid to the RASC for the handbooks. They contacted us. They sent out a letter of apology for all the mishaps and problems that they had with the 2022 orders. And the contact says, yes, I'll get that invoice to you, shortly, and I'm going to contact them right now. And that was 3 weeks ago or so, and still don't have an invoice for the handbooks. So I don't know if or when we're ever going to get it, but if we do, we're prepared to pay for it.
Probably about July, you'll get a past due notice.
Yeah, probably something like that. And then the usual expenses, our AT&T messaging for our hotline, even though we're not having open houses, we're still paying for that every month, and have the newsletter, print and mail costs, and then $50 Chili's gift certificate for Dan Durda for his talk last month. And that's what I have. Anyone has questions or whatever? Dave, I usually send an email to whoever's taking the minutes just to detail this stuff, because you might not have all the numbers, so I'll send
Thank
that to
you.
you tonight or tomorrow. Tonight or tomorrow.
Okay.
All right. That's my
Do we
report.
even want to know what temperature it is outside your door, Doug?
You do not want to know.
I thought so. Okay.
No.
Because it is cold up here.
Yeah, no, it's not cold. In fact, I was out birding and got home about 7 o'clock, and yeah, it's in the 70s. We'll just say that.
How many
Yeah.
new
Just found
species
out.
did you get, Doug?
What's that?
How many new species did you capture?
I haven't counted, but I probably added another dozen or more bird species to my life list.
Nice.
Yeah.
Shorebirds, and then some other things that are native to just here. Yeah, pretty cool. It's great. I will say one thing. We do have a member, I don't know if you know, I don't know how to pronounce his last name, Abe Orcott or something like that.
Yeah.
He just informed me that he recently moved to Florida. I don't know, he hasn't sent me an address or anything. I don't know where he is, but he's going to be an out-of-state member too. So.
Yeah, he posts pretty regularly to the Facebook astronomy sites, and he's been getting some marvelous images on the clear weather down there. So he's if you follow Facebook, he's on there.
His imaging is improved by leaps and bounds, and I think like Auni and some of the other Plymouth astrophotographers helped out along the way, and it just, he continued to get gear to help him, and his images start getting sharper and sharper and more detail. So yeah, he came right along after his first few shots. And also, you may recall, Abe had a daughter who was very interested in astronomy, and she was already better at observing certain things in the sky than I was the couple of times that we all came out.
Yeah.
Okay. So how about Jeff?
Tonight our peak was 33 viewers online, and we had a communications committee meeting on February 2nd of 22, so 2/2/22, pretty cool date. Mostly, I'll try to keep it short. We're going to move the youngastronomers.org into the collection of lowbrow domains, so that just makes it easier to manage. It's a lowbrow entity. It should belong there. Jack's been doing it for years, and it's like, it really doesn't belong here. So the other big discussion was basically revamping the website. And we decided we're going to go with a WordPress type of site. I've got the application I got to fill out. We're going to use Krishna's short code. It doesn't get charged, so it's not really a big deal, but that'll allow us to set things up. And the idea is basically to set up a parallel site so that we can move data from the old site to the new site, and at the same time organize it, which is kind of the other part of the meetings. We discuss like how to organize this stuff so it's not quite as chaotic, or, I don't want to say chaotic, that's a bad word, but basically bring a little bit of navigation, ease of use, whatever, to the site, so that it's easier for people to get to we got a lot of data in our site. That's been one of the problems. The other thing is to make sure we tie in Google Analytics so that we get a good idea where, where people are coming in, and maybe it helps us hone in on our audience a little bit better. And of course, things like open houses, events, things that are going on, announcements, that we wanted all to be kind of front and center, because that, after all, is kind of the primary purpose of the website. But it was a good meeting. I think it looks like it lasted about an hour and a half. It was me, Charlie Nielsen, Jim, Dave Jorgensen, Amy, Jack Brisbane, and Adrian were in that meeting. The minutes are in the folder in the Lowbrow Google Drive. So, and Dave, do you want those minutes and the access meeting minutes for your minutes for tonight or not? Oh, well, in any case, things are moving ahead.
So I did have a question that I should have asked when I snuck into the meeting on Wednesday, and it's refreshing the headshots. I know some of the historical headshots I figured we would want to keep.
Yeah,
but
the photos was one of those things. We've got a lot of older photos. We're going to have to collect new photos from people, because obviously we may have aged in the last decade or two.
Maybe.
But,
yeah. If you have somebody that can do headshots, I got the gear to do it. So
okay,
we can go with a free of charge quick. If we want to refresh the headshots, we can talk about doing that.
Yeah. And whether it's at an open house or at one of the meetings, I mean, both places have got nice clean walls and things that you can take pictures against. But our primary thing was like, let's get this thing organized. And then once we get the site up, it's going to be easier to delegate different sections of the old site to be moved in. And it's going to be a chore, but it'll be worthwhile, because what's going to be left, it'll look nice. And then we can basically transition to make that the primary dumping place for till the lowbrows will land. So landing place, there we go. Make sense? Any
Makes
questions?
sense.
Well, I got no further questions.
Okay.
I do have something to add, as long as you're on the website. More than one person has told me that Sky and Telescope, the instructions we have on the website are now probably not valid. So I need to take time away from birding or whatever I'm doing and actually investigate and have that updated. I think it was Ken Rubel.
You and me both. You and me both, Doug, because I got to do that for the Warren Astronautical Society. First one to figure it out wins.
The last time that I renewed, I was basically told, just because there's no online way to do it, you basically have to make a phone call and you talk to somebody and you give them the number and they give you the discount.
Yeah, and someone just told me that the discount has gone away. Now, I'm not positive that that's the case, because the normal channels that you would take, you would get a regular, some discount, but not the club discount. And it wasn't the $32.95 club discount that we've been enjoying for many, many years. So I don't know if that's a real change, or if someone, I have to ascertain that, whether that's actually the case or not.
I seem to remember it was like 35 or 37, something like that. It wasn't substantial the way it used to be, but it's better than 57.
Yeah, and someone told me it was like 43 or something, and it's like,
that doesn't sound right. That
doesn't sound right. So I need to find it, and I need to find out.
Well, that's what they told me anyway. That's why I paid.
It's always been kind of flaky with them. It's after the thing got sold, I don't know, it's been sold a couple times now, and it's unclear exactly what you need to do. So I'll get to the bottom of it, and I'll get the real answer, and I'll make sure it's updated.
I can't remember who gobbled them up, but they've gobbled up Wilman Bell, and so
it's the International Astronomy Association.
Yeah, that's the most recent.
Society. Yeah, they own it now, and they're doing all the fun operation.
Okay. How about Jack?
Oh, I'm going to go to screen share. And if this works. Okay. And as you can see, this is the road to the radio observatory. I was out there yesterday. Well, I should say the 16th, which would be Wednesday, I believe it was. And here's the other one. As you can see, I went out there. Everything's fine internally in the observatory. No more spray painting or anything like that, vandalism on the walls or stuff like that. And
Yeah, too cold.
well, yeah. Too cold.
One thing about the little kids, they're not about to struggle for any reason, even the paint.
So I'm waiting. We're going to work on our open house dates, which I'm looking at, sometime March, April, hopefully. We can have an open house, start our open house again. I have checked out the observatory internally with the telescope and everything else. We should be okay. And that's all I have to say right now. I've just been monitoring the situation and waiting for us to have our open houses, and based on the weather and the working with the weather wizards to tell them to turn off the cloud switch so we can get clear skies. Other than that, I'm just waiting for things to change so we can go back to our open house status like we used to do.
I'm gonna have
Any
to learn the
questions?
telescope all over again. Does anybody have anything else? Do I hear a motion to adjourn?
Motion to adjourn before I think of something else.
There you go.
Accepted. I support.
Okay. With that, we are adjourned at 9:41 p.m. Thank you very much, and we'll see everybody in March. I think our first scheduled open house is after our scheduled meeting, so probably the meeting first, and then hopefully an open house right after that. So take care, everybody. Have a good night.
Take care.
You too, Charlie.